Huh? What? Continuity corrections. What is this? Well, in short, it's a topic we should have covered directly after we did normal curve. I basically forgot. Sorry. Luckily, it's a pretty easy one. It's a small adjustment on normal curve problems. And as long as you understand the normal curve process, you just make this little quick adjustment and you're good. So let's talk about what this means, what the heck this word means, this picture, etc. Okay. Tom Cruise. All right. What's the issue here? The issue is two types of data. Continuous data and discrete data. Now, what do these words mean? They're a fancy way of saying datas that can have a decimal and data sets that everything doesn't have a decimal, aka a whole number, or a better way to say it, an integer value. So some data sets you can have decimals, continuous data. Some data sets, it doesn't make sense. All the numbers are integers. And you could probably think of some very quick real-world examples. Why? Continuous data, something like height, weight, even age, you could have decimals. You can be 5.73 feet tall. Discrete data, integer only, these are things that you can't cut in half, sometimes literally. Most common one is the amount of people that do something. You can't have half a person. So, let's look in the book. This is page 172, where they briefly explain this stuff. Let's take a look at what they want us to do when data is discrete. So this implies the way we've been doing it with continuous data when decimals are okay is fine, you don't change it. We only do this little change for discrete data. So I'll be direct, real quick. The changes for discrete data, sometimes with your x value, you don't plug that into the z-score formula, but instead you move it to the left or to the right 0.5. In the book, they do like a cursory explanation of why we do this. And it's kind of similar to when we were talking about doing a histogram, how sometimes because of decimals, you don't start the bar of the histogram right on an integer value. Here we see one right here. Here's 110. To the right, 110.5 and 109.5. Why is this? Because decimals in between 110.3 would round down to 110, or 109.7 that would round up to 110. So you more so straddle the integer with the bar of your histogram. Well, under the normal curve, even though we draw it normally as like a smooth curve, what they're saying is really what's going on here is you could think of it as you have a bunch of bars, rectangles. And I could explain this a lot better next year when we get into calculus and we talk about integrals, Riemann sum, stuff like that. Although we did hit the RAM method this year, I think. So it kind of makes some sense. The idea is the area of all those rectangles should add to 100%, or close enough, 99 point whatever percent. We know that the tails of the normal curve are asymptotic. So the idea here is when we're trying to set certain x values, sometimes you have to go a little more to the left or right to make sure all your values fill in the correct category. And the simplest way to think about it is by rounding. Okay. Well, let's talk about some examples real quick from the book, and I'll just go through them. We're not going to talk about how to do them. Nah, not at all. We're just going to talk about identifying data as continuous or discrete. So going backwards in the book, here we see ACE problems. How do you know your ACE problems? Because They have this bold type under them telling you what ace paper it came from. And in general, that's why this is a good book. These are the most important problems to look at. So let's look at these, and we'll talk about how all of these are continuous data sets. Here's one. Tire pressure, tire spelled with a Y. What is wrong with these British people? They said it's measured in bars, 1.9 bars standard deviation. They're already implying bars can have decimals. Okay? The length of fish is 38 centimeters. Can you have a fish that's 38.5 in length? Sure, makes sense. Here's one, number 19, where they don't tell us the context of the problem, but they say x is greater than 5.2. So if they don't tell you you're dealing with discrete data, you can assume it's continuous. That's cool. Down here, we have the amount of days an infection takes to clear up. Can you have half a day? Sure, that's 12 hours. Boom, there's continuous. Looking over here, other examples I'm seeing are temperature. Can you have 87.5 degrees as the temperature? Faux sure. All right, let's flip to the right and let's look at some data sets that are discrete, perhaps. Okay. A large sample of flapper fish are taken. The x values represent fish. Not that problem before when it was the length of a fish. This is actual amount of little fishies, and I guess you could cut a fish in half, but if you're counting whole fish, we don't want to. Okay, to emphasize that point, we have a problem about dogs, and the population counts as dog owners, thus people. You can't cut a person in half. We want integers only for this. Number 5 is about questions on a test. Multiple choice test at that, and that helps because can you get half credit on a test? Yeah, some tests. Can you get half credit on a multiple choice test? Nah, it's usually all or nothing. Thus, this is discrete data. Telephone subscribers, that's people. Here's one with people. Adults, people. Vehicles, trucks. I guess you can't drive half a car around. Okay, so hopefully that proves the point. That's how you identify, okay, I have to do this shifting. So here's what it looks like. I have 3 quick examples. We don't even have to do them. We just talk about the setup of the problem. So say it's a normal curve problem, and they're asking you to find the percent to the left of a certain data point. Here I'm saying the mean is 10, the standard deviation is 3.1, and the data set, or the data point they told you about was 7. So they want the percentile of 7. They want this percent right there. Now, if they've implied in the problem that the data is discrete, say your amount of people, and we don't want to cut a person in half, this is how you'd adjust it. Rather than 7, which we see right here, we want to go slightly to the right and set our x value at 7.5. Why is that? Because we want the percents that are in between 7 and 7.5 to round down and count with the 7. And so into your z-score formula, rather than 7, you would start with 7.5. From here, it's just the same process as always. You'd find the distance and the amount of deviations. You'd use your table to turn that z-score into a percentage. That's all it is. This one's to the left, so we'd have to do 1 minus the positive version, etc. Okay, what if they asked for percents now above 7? They might say to the right, they might say above, they might show you this notation with the inequality. So that means we're looking at this type of picture. So notice it's the same number, but now since we're going to the right, decimals like 7.2, 7.3 from up there, well, of course they're going to count. They're to the right. Now we want to make sure that the decimals to the left of 7, in between 7 and 6.5, that those would get included on 7. So rather than start with 7 in our formula, we start with 6.5, and you do everything else the same. Find the z-score, find the percent, minus the percent from 100 because we're wanting to the right here for this one. So notice, this one's 7, but notice how we start with 7.5 when we're looking percent to the left, and 6.5 with percent to the right. Say they gave you one where they want the percentage between two data points. Normally our process is you just find the percentile for one, the percentile for the other, and you subtract them. Okay, that's true, but rather than 8, since we want percent to the right of 8, we got to go down to 7.5. And rather than 11, since we want percent to the left of 11, we got to go up to 11.5. So our two formulas over here, z-score formulas, notice you don't start with 8 and 11, instead 7.5 and 11.5. And from here, you know, ... You can try this at home if you'd like, but you just find the z-score with both the percents that go with those z-scores. Notice 1 is to the left side of the normal curve, so you'd have to minus it from 1. And once you get those two correct percentages, you just subtract them, and there's your answer. Okay, so there's that little adjustment. You could think of it as, yeah, the time where we move 0.5. You don't have to call it continuity correction. It doesn't matter what you call it if you know when to do it. And when do we do it? Right here. Discrete data. Importante, importante. So now for every normal curve problem, you really need to ask the question, wait, is this continuous, or can we not have decimals? Is it discrete? If so, you're going to have to do this 0.5 slight bumps. Have we done problems wrong? Maybe a little bit. There was one on the quiz about memes. You can't really look at half of a meme, so that problem probably should have had continuity correction. Okay, so there it is. Identify discrete data, bump it over 0.5 to the left or the right, depending on the picture. Peace out, rainbow trout.